Okay, welcome. This video will go through ballooning equations and ballooning modes. And so I'll introduce what happens when you have a localized instability, which occurs just localized on a single flux surface, how you order this, so how you introduce this into the delta W equation. And you end up with several orders, and the lowest order gives you the shape of the fluctuations, which are long and thin along field lines, and very small across the field lines. And then using the next highest order, you get an equation for the ballooning mode in terms of a single potential, and that will be the starting point for the next lecture after this. So we start by writing down the delta W equation. So these are the field line bending terms, the compression terms for magnetic field and the pressure, and then the curvature drive, the pressure, and the kink drive, the current. And then the perturbed magnetic field is given by this expression, where psi is the perturbation, and the perpendicular component of it goes into this. Okay, so now we're going to consider perturbations which are localized, and so what we have is that the gradient is large, and so we have a gradient of the perturbation of any component divided by its magnitude. It's going to be a large quantity, so it's going to be like 1 over epsilon, where epsilon is small. And so the gradient is large, and then this is large compared to the background equilibrium quantities. So equilibrium so for example, magnetic field strength, did the same thing for grad B. This would be like order 1, for example. And so the gradients of fluctuations are small, so the fluctuations are narrow, so the gradients are large compared to the equilibrium. So we have, for example, the minor radius, we have the pressure, we have some kind of pressure profile. What we mean here is instabilities which are highly localized around a particular surface. So they might be very, very narrow, but the gradient is very large. And the gradient is much larger than any kind of equilibrium profile. Okay, and this allows us to order these quantities. So I'll write down here. So this is a gradient of the perturbation, and so this is like this is a large quantity, so this is order 1 over epsilon. And so this term here is like 1 over epsilon squared. This is a large one. This quantity here, for example, psi is small, or not a very large quantity, and so this term here with the gradient is much larger than that one, and so this we can essentially neglect. This term is of order, well, you've got 1 over psi and then squared, so this whole thing becomes 1 over epsilon squared. Same for this here, so this is 1 over epsilon squared. This term here, now so these are all of order 1, so there's no gradients of the perturbation. So this term is roughly of order 1, but in fact it can be neglected. So if we're looking at modes here which are localized around a surface, we're integrating over the whole volume. Actually, this ends up being the surface integral, and this goes to 0 at the surface. So we just integrate over a large volume, and the mode is in the middle, and this j is slowly varying. And so this term, actually, we're going to neglect this term entirely for now. So just purely looking at ballooning modes driven by the curvature of magnetic field, without any kind of kink or peeling component. And this is reasonable for modes which are very narrow and localized. When you have a kink mode, this tends to be much broader and involves a larger radial width. Okay, so now we can take the largest terms in this equation. So we have these 3 terms which are of order 1 over epsilon squared. These are the 3 largest terms. And we have, I'm going to label it, so the delta W equation, I'm going to label the order in here as here is -2. So first we're going to minimize this equations, the three largest components, so order 1 over epsilon squared. As usual, this is the only term which involves any parallel perturbation, and so here we just choose the parallel components, so choose psi parallel such that this term can be ignored or go to 0. So that term I'm going to set to 0 by choosing psi parallel. Now we can make a reasonable guess to what the perturbation should look like. So if we have something which is like ideal MHD, we basically have E cross B motion of the plasma. You can show that this actually is the motion that minimizes this quantity, and so you can write that the displacement of the plasma is the perpendicular component of it, because we're choosing the parallel component to minimize this. So the perpendicular component we write as. And now we can think about what the orders are in terms of these powers of epsilon. So if these are second order, it means that this epsilon is order 0. It's the 0th order. So then these are taking two derivatives and getting psi squared. And now this is a large derivative, and so that is like a 1 over psi. And so this must be a first order term. So it's first order in epsilon. And this is going to be an expansion, so we're basically ending up with an expansion where the plasma perturbation is sum of a set of terms which are getting increasingly smaller. So we have correction terms. So in principle this would be an infinite series. Each term, so this term is order 1, this term is order epsilon squared, and so on. Right, and since epsilon is a small value, each of these terms is smaller than the last. I guess if you put this into this term here, what we end up with is that we have the perturbed magnetic field. So if you put this expression in for sine naught into this term here, you end up with this expression. And now what we can do is the phi, this phi which appeared in here, side was order 1. Now to get rid of this, or as a second order contribution, what we need to do is make this small. So somehow we need to make this of order 1. So if this is of order epsilon, so this is a gradient which includes all three directions, so across the magnetic field as well as along it, and so this is of order 1 over epsilon. And so with just these two terms, this is of order 1, so this will cancel with this one. So with this derivative here, we have a b dot grad, so it's a derivative along magnetic field. If this is of order 1 over epsilon, for example, then this whole thing would be 1 over epsilon squared, and that's what we're trying to get rid of. So if we make this instead order 1, so we choose the perturbations in phi, so that along the magnetic field the gradient is small, then this whole thing becomes of order 1. So summary delta B perpendicular squared is of order 1. So if we have the b dot grad of phi is of order 1, and this means that the equilibrium gradients of the perturbation are on the same scale length as the plasma itself. And so this makes some physical sense. If you try and draw in a tokamak, we have something which has some structure in the poloidal plane. So we might have some kind of mode number on the outside, but along the field lines, the gradient in this direction is very very long. So the mode has some kind of structure, but it's varying on the equilibrium scales, not on the small scales. So these small scales are small, but this b dot grad is roughly 1, so b dot grad across here, whereas across this direction in the poloidal plane, we have the gradient is roughly 1 over epsilon. So gradients in this plane are large, gradients along this direction are small. So that's the main result of looking at the 1 over epsilon squared is this term here, so that we have the parallel gradients are small relative to perpendicular gradients, and we have the form for the perturbation here. So the perturbation is essentially like an E cross B kind of a drift with some potential field phi, and that's eliminated this 1 over epsilon squared term. So this is the largest terms. So if we go back to the delta W equation now, we eliminated this term by choosing psi parallel. We've reduced this term from a 1 over epsilon squared to just an order 1 term, and then we've also eliminated this term by this choice of perturbation. And now we're left with essentially these terms to include. So we have a delta B perp and a pressure term. So the terms that show up at order 1 so are still this one, and this one. So just write them out again. So this is the order epsilon to the naught. So here we do a similar trick to before. So we just essentially choose one of our perturbations. So we can we have a power expansion in psi, and we can essentially choose our psi 1 because this is order 1 over epsilon. We can choose epsilon, the psi 1 term here, to cancel this term out. So having chosen psi 1 for the perturbation to cancel this one, we just left with these two terms here, so the field line bending term and the pressure drive term. And so I'll just write out these in what these are. So substituting the expression for delta perp, B perp, and the expression for psi perp that we had previously up here. So we'll put the 0th order perturbation into this equation. So this is the field line bending term, and remember that these derivatives here, so this is derivative which includes across the field lines, and so this is like 1 over epsilon. This is a derivative along the field lines, and so this one here is of order 1. And these are derivatives across the field lines. Well, here you've got a cross B, so this is across the magnetic field, and so these are both large terms. And so now what we're going to do is we're going to minimize this term. And so we just label everything in here inside the integral. Just going to label this whole thing L. And then we just use the Euler-Lagrange equation, so we just have the dl by d phi and the divergence of L by d grad phi. And that's for the variation of delta W0 with respect to the perturbed potential. And so this we can use. So there's no phi explicitly here, only gradients of phi, and so this term is 0. The next term you get some stuff from here, and terms obviously from here and from here. This term takes a little bit of looking at. One way of deriving it, I'll show you quickly here. So here I've done, this is the functional derivative of this expression, so the modulus squared of the gradient of b dot grad phi. And here I've just done it with delta functions, so it's a bit of an abusive notation, but I hope it's reasonably clear what this is doing. You'd also do it by expanding this out as a function, which adds a perturbation to, and end up with the same result. So we make a small change to the function, and then see how take the difference with the original. Again, propagate this through, so you end up with basically the derivative of this. So you end up with a factor of 2 here. You then integrate this by parts, so integrating this part and differentiating this second part. And this gives you this integral here, so you end up with the second derivative from this, and you end up with this term here. Again, this bit of abuse notation with the delta function here, but this is basically because this is in one space, like a x prime, and this is x. So when you integrate this delta function pulls out a particular value of this expression at a given x, and so here you just get a b rather than a b dot with this delta function here. And you end up with a second derivative because you had to integrate by parts this part here. And so this term here from delta b perp ends up with a second derivative term here. And so the whole thing, the second part takes quite a bit longer, but the end result is this. So you see this first part here with the second derivative has turned into this. There's a b, so the divergence of this whole thing, because the divergence of b is 0, you can take the b outside, it becomes a b dot grad, so a parallel derivative of this part here. This part here takes a lot of manipulation to get this form, but it's relatively straightforward. And then this gives us an equation with a single variable, so a single scalar field phi. And if we solve this equation, then we can work out the envelope for a ballooning mode, and this equation can be manipulated further and simplified further and used to calculate the stability of a plasma. And so you'll see in the next video I'll go through and use the ballooning transform to simplify this into a 1D equation.